Hi everyone, welcome to our video lecture on section 8.8 dealing with numerical integration. Now, in the past couple of sections, we have talked about different integration techniques that can help us evaluate many different types of integrals. But the fact is that some elementary functions simply do not have antiderivatives that are elementary functions. Now, if you need to evaluate a definite integral involving a function whose antiderivative cannot be found, then you may need to use an approximation technique. Now, there are many such techniques, but in this video, we're going to be discussing 3 of them. Now, the first technique you definitely had back in Calculus 1, but it does bear some repeating. So let's go ahead and begin here with Riemann sums. In Calculus 1, you learned to approximate the area under a curve using rectangle approximation. You may recall that these rectangle approximations were often referred to as Riemann sums. So let's go ahead and review those with the following problem. So example 1 here is asking us to approximate the area, rounded to 3 decimal places, of the region bounded by the function f of x equals to e raised to the negative 0.1 x squared, the line x equals to 1, the line equals to 3, and the y-axis. Now we will want to approximate this one here using 4 left endpoint rectangles with equal width. Now before we jump into the approximation, why did we want to approximate this integral? Well, the reality is that none of the techniques that we have learned so far will help us integrate this function. I mean, truth is, there is no integration formulas that can be used because e raised to negative 0.1 x squared does not have any elementary function as an antiderivative. Now in chapter 10, we are going to look back at another strategy for doing this, but this one here would also be an approximation technique. So let's go ahead and jump straight into the approximation then. Now, the way that I want you guys to start this problem here is by first making a sketch. Now, how exactly does this function look like though? Well, lucky for us, we can go ahead and use our calculator to take a look at how the graph would be looking like. And in fact, we're going to be using the calculator for a lot of these calculations because, well, it's a numerical approximations, so we are going to be using the calculator quite a bit. So let's see here. If I want to take a look at the function here, I'm just going to go to the y equals to, type in the function, and we're going to get e raised to the negative 0.1 x squared. So let's see how would that look like. Alright, so we really can't appreciate the graph all that much, so I'm just going to be changing the window because we're only interested in the area between x equals to 1 equals to 3. So going to our window here, let's go for 0, 1, well, going all the way to 3. And, well, it seems like we did not have any negatives. So for the y min, I'm just going to set it here at 0. And the y max, well, I'm just going to go ahead and set it to, I don't know, maybe at 2. So let's see how the graph looks like. Okay, well, there we go. So let's go ahead and make a sketch here. There we go, here's my sketch. Again, it's just a sketch, it doesn't have to be perfect. So I'm going to go ahead and highlight the area of interest. Okay, so we're interested in the area right over here. Alright, so how do we approximate the area? Well, since we want 4 rectangles of equal width, then that means that the total length here between 1 and 3 has to be divided by 4. So what's the distance here between 1 and 3? Well, the distance between 1 and 3 is 2. And if we're going to be dividing it by 4, then 2 over 4 is going to be 1/2. So that means that essentially we're going to be selecting 4 subintervals of a width of 1/2. So we're going to have here then one rectangle here with a width of 1/2, another rectangle here with a width of 1/2, and another rectangle right here with a width of 1/2. Now, for this problem, I figured out the width just thinking about it, but lucky for us, there's a formula that we can always use. So the formula to figure out the width is the following, and you might remember it again, very similar to what we discussed here with the disk and the shell method. We're going to have here that delta x, the width of our rectangles, is going to be b minus a all over n, where the a is our left endpoint and the 3 is our b, which is the right endpoint. Now let me give myself a little bit more room here on my sketch so I can label it appropriately. Okay, so now we figure out our width, which was the delta x. So this one here, each subinterval has a width of delta x. Alright, now remember that the area of a rectangle was equals to the base times the height, and at this point we do have the base was delta x, but what about the height for the rectangles? Now, this is where the instructions play an important role. We're looking for 4 left endpoint rectangles. Now, what that means here is that you're basically going to be using the left endpoint to start off to select the height of each rectangle. So we're going to pick here our first rectangle. The left endpoint here was given in 1. So this is what we're going to be using to select our height. So we go here, the left side of the rectangle, there we go. This is our height. So what is the height? Well, remember, this point right here on the graph is given by f of 1. So there we go. This one here is determining the height of our first rectangle. Now continuing it here, there we go. That's our first rectangle. Now for the second rectangle, again, now we're going to be, you can see the rectangle right here. That's the second one. So how do we determine again the height? Well, we pick the left-hand side of, or the left side of this rectangle right over here. So this one, the height is given now by f of, well, which one is our x-coordinate? Well, if we started at 1, and then we went a delta x of 0.5, this one here is going to be 1.5. That's giving us the height of our second rectangle, getting the height of the third rectangle. Now picking the left-hand side again, right over here, f of 2, going all the way to the other rectangle. Look kind of ugly. There we go. And this height for the last one is going to be given by f of 2.5. And there we go. Now you get to see here that this approximation of the area is not too good because, well, there's some regions that, well, they seem to be above the curve. So this one seems like an overestimation, but, well, ultimately it is an approximation, so it doesn't matter too much because we are taking the fact that it's an approximation into account. All right, so as you can see here, the height was given by the function value evaluated at different axes. Okay, so in order to approximate the area, then we need to figure out, okay, well, what's the area of each individual rectangle? And then we can go ahead and add them up. Okay, so the approximate area is going to be area 1 plus area 2 plus area 3 plus area 4. Now, putting this one here in terms of delta x's and the function values, we're going to have here a delta x times f of x1. Well, since every function here for the area has a delta x, I'll just factor it out here. And again, this is just a review for Riemann sums. So we're just going to have here f of x1 plus f of x2. Well, might as well do this one here in one go. It was going to be the original, or the first height, I'm sorry, f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. And there we go. So what are we going to get here? Well, let's see. For our delta x, we had a, what was it here? I believe I erased it, but it should have been a 1/2. So we're going to have a 1/2 times. Now, this is where the calculator is going to come into play. So let's go back to our calculator. Okay, so this is the way that I want you guys to do the problem. Now, we've already put in our function here in order to graph it and see how it looked like. Now, rather than going to the calculator and putting in the function and evaluating it in 1, what I want you guys to do is make use of the capabilities for the calculator. Now, the calculator can actually store a function and evaluate it without the need for us to type everything in. So this is what we can do. If you have this newer types of calculator, what I want you guys to do is click on alpha. Well, let me just clear it so you guys can see it. So I want you guys to click on alpha and then click on trace. So once you do this, you're going to see here a menu pop up that tells here y bar. Now what I want you guys to do here is essentially select our function y1. So click on 1 here, and there you go, y1, because this one is, oops, this one here is our y1. It's e raised to the negative 0.1 x squared. All right, so treating it just as a function, I want to evaluate y1, so I'm just going to put here y1, which will evaluate y1 at 1. And there we go. It is giving us a value. So we can do this one here in one step by, again, just going, so alpha f4, y1, evaluated at 1, plus, now we repeat the same step, but now we're going to be evaluating at 1.5. Now, in case you don't have this newer types of calculator, no worries, we can still do it. It's just going to be a little bit longer. If you want to access the y functions, you need to go to the vars option or the vars button. So click on vars. Now you go to yvars. Now you select their function and we pick, well, which one were we looking or which one were we using. We're using the y1 here. So there we go. Put it at 1.5 and so forth and so forth. So I'm just going to go ahead, click on the other ones. And there we go, guys. I typed in all the other ones. Now click on enter. And there we go. We have a 2.9089. Now at this point, sorry about that. Now, since we're still multiplying by a 1/2, I'll multiply everything here by a 1/2. Let me just read it here. Put it at 1/2. All right. So multiplying this by 1/2 or 0.5, we're getting approximately a 1.454. All right. So our answer, it was approximately 1.454. And there we go. Now, to be honest, this doesn't look like a very good approximation because, again, we only use 4 rectangles. However, as you know, if you wanted to get the exact area underneath the curve, well, then we would just need to evaluate our Riemann sum with an infinite amount of rectangles. But, well, that was just going to take us to our definition for the definite integral. Okay, so now let's take a look at another approximation, but this time around using 4 midpoint rectangles of equal width instead of left endpoints. And let's see what we get there. Now, as usual, we want to go ahead and begin with the sketch. All right, so now that we have our sketch, same idea here, we're going to go ahead and calculate our width. Now we know here that the width was, we're still dealing with the same problem. So our width was 1/2, but yeah, just to recap, it's just b minus a all over n, which in this problem here is going to be a 1/2. Now, the only difference here compared to the left-sided endpoints is the way that we calculate the height. Whereas before with the left endpoints, we created our rectangles, and in fact, I'm going to go ahead and draw them again. So 1 and 1.5 would be over here, so that's one subinterval. Here's the other subinterval. Here's our other subinterval. Now, to calculate the height, we're essentially going to be picking the midpoints in our subintervals here. So what is the midpoint between 1 and 1.5, which is right over here, 1.5, 2.5 right here? Well, the midpoint between 1 and 1.5 is 1.25. In fact, let me just go ahead and move this one here further up. There we go. So we're essentially going to pick this midpoint right here at 1.25. Now for this problem here it was easy to see that it was 1.25, but well, what if we're dealing with other subintervals and it's not as easy to see? Well, remember that you can always calculate the midpoint by adding the two x's and then dividing them by 2, essentially finding their average. So for this one here, I'll put x1 plus x2 divided by 2. So for example, in this particular subinterval, our x1 was 1 plus 1.5 divided by 2. That gives you 1.25. All right, so with this 1.25, we are going to be calculating the height. The height right here is f of 1.25. And now we can form our rectangle here. And we're going to be doing the same thing for the other subintervals. So what is the midpoint between 1.5 and 2? Again, we can go ahead and use our midpoint formula, but there's a quicker way. Now remember that we're still dealing with an equal width for our rectangles, so what we can do here is simply take the 1.25 and add the delta x, which is 1.5. So what is 1.25 plus 1/2 or 0.5? Well, it is, I'll put it here, a 1.75. And we can go ahead and repeat the process, keep on adding our delta x, and that's what's going to go ahead and determine our heights. So I'll just put it here. That's another height. There's another height. And this is another height. Now, if we visualize the rectangles here, you get to see here that, okay, well, it looks like it's a better approximation it's a better approximation when compared to the rectangles that we selected, or the rectangles with the left endpoint. There we go. And here's our last rectangle. Okay, so to calculate the area, it's going to be the same idea. The area is going to be equals to the width, 1/2, times the sum of the heights, which was the function evaluated at the midpoints of the subintervals. Alright, so now once we've set up our formula for the area, let's go ahead and figure out what is this area using our calculator. So, same idea here. I'm going to go ahead and keep the same operations, except that I'm going to be switching the endpoints. So I'm just going to go to our calculator, and I'm going to go ahead and go back to the previous operation. So second enter. There we go. Now I'm going to go ahead and edit them. So let's see, our first height was the function evaluated at the first midpoint of the first subinterval, or the midpoint of the first subinterval, which was 1.25. So rather than deleting everything, what we can do to tweak it without removing anything, we can just go ahead and click on second and insert. So let me just clear this so we can see it. So let's see, I'm going to click second and then delete, so we can now insert. And I'm going to put a 0.25, and I'm going to go ahead and repeat the same thing for all the other function evaluations. So again, second del, so we can insert, and now it's the function evaluated at 1.75. Okay, so I'm going to go ahead and repeat those. And there we go, guys. I changed the inputs now. So you see here now it's 1.75, 2.25, and lastly a 2.75. Click on enter, and we get a 2.6637. Now we still need to multiply this one here by 1/2, so times 0.5, and we get a 1.3318. So our area is approximately 1.332. And there we go. Now when you compare it to our previous problem, which gave us a 1.454, I think this one here again is more accurate because, well, there's less of an overestimate here. Now, let me show you guys this on Desmos. Okay, so here we have a better visual representation of the approximation of the area. Now, using 4 left endpoint rectangles of equal width is giving us more area than that's actually underneath the curve. Now, it is true that we could go ahead and add more rectangles, so I'm going to go ahead and increase the number of rectangles all the way to, I don't know, just 50, for example. And yes, okay, it's a lot better. It's still not that great because, well, there's still an over approximation, but okay, I'm not gonna lie, it is getting better with more rectangles. But let's go back to 4 here, and I want you to compare it here with the midpoint formula or the midpoint approximation. So I'm gonna go ahead and switch this one here to a 0.5. There we go. This is now the midpoint sum. And we get to see here that there's still some parts where you seem to be overestimating, but it is balanced out by some of the parts where you are actually underestimating it. So because of that balancing out, you actually get better approximations. Alright, so this is where we're going to be stopping part 1, and we're going to be taking a look at more approximation techniques in part 2 of this video. See you there.